idea who could possibly be coming. All right, so we are moving on to chapter 4, and we are talking about extreme values. What could that possibly mean? Okay, peaks or troughs, highs and lows, things like that. That's exactly what we're going to be talking about. So one of the most useful things we can learn from a function's derivative is whether the function assumes any maximum or minimum values on a given interval and where these values are located if it does. Knowing how to find a function's extreme values, called optimization, enables us to find practical real-life information such as the maximum profit in a given situation or the minimum surface area of a container. Okay, so optimization is a huge application of calculus. So the last chapter was all about how do we take derivatives. Now this chapter is all about what can they be used for. And optimization is one of the biggies that we use calculus for. Okay, so definition. Absolute extreme values. Let f be a function with domain D. Then f of c is the absolute maximum value of D if and only if f of x is less than or equal to f of c for all x in D. It is the absolute minimum value of D if and only if f of x is greater than or equal to f of c for all x in D. What does that mean? Okay, so f of x is a y value, right? So it's just saying that this y value is an absolute max if everything else is lower than it. It's an absolute min if everything else is higher than it. Okay, so what would have an absolute max? Well, something as simple as an upside down parabola. This point that we call the vertex would be the absolute highest point because every other y value is lower or less than. Now, notice that it says or equal to. Okay, so what if I had something that was kind of like an M? Then I could have two absolute maxes there. Because these are equal to each other just means that they're both maxes. Okay, so that's why it says less than or equal to in the event that there's more than one. And then absolute min is just the opposite. It is the absolute lowest point on a graph. So like something like this, I would have one y coordinate that was smaller or lower than all the others, so that would be the absolute minimum on that graph. Okay, so contextually, it's an easy concept. This makes it sound really hard. Absolute max and min values are also called absolute extrema. Well, that kind of makes sense because they are the extreme high or the extreme low on the graph. Extreme value theorem says that if f is continuous on a closed interval, okay, so what that means is you have some graph that has no break in it, but it starts at one x value and stops at another. The domain is not all reals. It goes from one x to another x. Then it will have a max and a min value. Okay? Now, if the domain is all reals, that doesn't hold true. Think of this graph right here. Does this one have an absolute max? No, because it continues on forever. But if I said, okay, we're going to only look at this graph from this point to this point, then would I have an absolute max? Yes, that point right there. Absolute min would still be this one. So this extreme value theorem says if you have a closed interval like that, then there will be a max and a min. But if the domain is all reals, not necessarily. Okay, the minimum value and or maximum value may be at an endpoint or an interior point of the function's domain. So taking this example that I had right here, stopping it at those two dots, the maximum is at an endpoint, that one right there. But the minimum is what we call an interior point. It's not at an endpoint. Okay, so that's all that's saying. They might be at the very ends or they might be somewhere in between. Could be anywhere. Definition of local extreme values. All right, what do you think the difference is between an absolute extreme and a local extreme? Not necessarily. Let me show you this one, right? Go back to this one. This one has a local max and an absolute max. That one right there, yeah. So local means like in its neighborhood, it's the highest point. In its neighborhood, it's the lowest point. So locally, it is the highest or lowest, but it's not the absolute highest or lowest. Okay? So that's what local means. Sometimes we also call them relative, and I will use both terms interchangeably. So local or relative maximum. If and only f of x is less than or equal to f of c for all x in some interval. Means like in the general area of. Local minimum, same thing. So it's just saying in a particular region, it's the highest or lowest, not necessarily the absolute. Okay? All right, so looking at these. And these four graphs that we're looking at have definite stopping points, so we can put little dots there if that helps remind us that these are not continuing on, so the domain is not all reals. This one has a maximum and a minimum at interior points. That just means not the endpoints. That would be a relative or absolute max there. Yeah, so that one would be an absolute max. That's how we can abbreviate it. This one down here would be an absolute minimum. Would I have any relative max or mins? Or local? The endpoints, yeah. So in this region, that's the lowest point, but it's not the lowest point on the entire piece of the graph. So I would call this a relative or local min. And then this endpoint over here, in this region of the graph, it is the highest, but it's not the absolute highest. So this is a relative or local max. So you can have both things going on at the same time. Okay, this one has a maximum at the endpoint and a minimum at the endpoint. Do I have any relative or locals? No, those are it. Okay, this one has a maximum, the absolute max, at the top of this, what looks like maybe a piece of parabola. Okay, I do have a, oh my gosh, look at this. She said you'd be here at 8:30. Oh my goodness. Well, congratulations on your win yesterday. Absolute minimum here. And then would this classify as anything? Relative min. It is the lowest point in that area of the graph, but it's not the absolute. Okay, this one has a minimum at an interior point, a relative max at an endpoint, and an absolute max at an endpoint. So, moral of the story is they can occur anywhere, at the endpoints, or somewhere in between. Okay? All right, so this one down here has a little bit of everything going on. So we'll just look at this. So, and again, this is a closed interval. So it starts there, stops there. Absolutely the lowest point on the graph. So absolute minimum. That's a local max. Highest value of any nearby. Local min. Absolute max. Local min. Okay? Tell me about the derivatives at this point right here. Slope is 0 there, right? What about right here? Slope is 0. What about right there? Okay, it's undefined, isn't it? Because that's what we call a cusp. So these places that are not endpoints will be of interest. We'll talk about it in just a second. Where the slope is 0 or where the slope is undefined, because that's where your peaks and your valleys are going to occur, wherever you have these turns where you have a slope of 0 or these sharp edges where we have corners and cusps. So those are the important red flags that might signal a max or a min. Okay, so in figure 4.4, notice that the interior local extreme points are points where either the derivative is 0 or the derivative does not exist. We usually only need to look at a few points to find a function's extrema. We need to look at the interior domain points where f prime is 0 or f prime does not exist, and the domain endpoints. Okay, so critical points are what? If I say we're going to find critical points, what would that mean? Okay. We're looking for maxes and mins, right? Okay. And local, absolute, both are important. And those will occur. A point in the interior is where the derivative is 0. The derivative does not exist. Those will be critical points for us. Those will be points of interest. Okay, but we're also going to have to check those endpoints. Because look at the endpoints. This was a local min. This was an absolute min. But the derivative isn't 0 here. And the derivative isn't undefined here either. So in addition to looking for where the derivative is 0 and undefined, we have to also check the endpoints. So a point where the derivative is 0 can be referred to as a stationary point. Okay, that is a word that your book will use a little bit. Point. Anywhere where the derivative is 0, referred to as a stationary point. Why do you think it's called a stationary point? It makes sense if we think of it in one respect. Okay, let's think about also, what if I have a function that represents position? What is its derivative representing? Velocity. When that first derivative is 0, your velocity is 0. What's happening if velocity is 0? You are not moving. You are stationary. Okay, so stationary point just means the derivative is 0. Okay, in summary, extreme values occur only at these critical points. Where is the slope 0? Where is the slope undefined? And at the endpoints. Those are the only points we're going to check and be interested in. Okay, here is the graph of x to the 2/3. What does x to the 2/3 mean? Cube root of x squared. It's another way of writing cube root of x squared. Now it's a little lopsided looking only because notice the domain is going from -2 to +3. So if I went from -2 to 2, it would be symmetric like that. So it kind of reminds me of like bug antennas, this graph. It like from the origin it goes out like this. Okay, kind of like little antennas. Okay, so here is the graph only from -2 to 3 on the domain, and then the range that is showing on this window screen is from -1 to +3. Okay, so if we graph it, we can see that we do have an absolute minimum value at 0, 0. What is the derivative there? It's undefined, because technically, as we're coming in closer and closer with this curve, that the tangent there is vertical, and the slope of a vertical is undefined. Okay, so, and an absolute maximum of approximately 2 at x equals 3. And I am just basing it on this graph looking like 3, 2 there. Okay? And so that would be considered an absolute max. If we analyze the function algebraically, we look at the endpoints and the critical points and compare the value in each. Okay, so if we're doing this algebraically, this is what we're going to do. We're going to take our function, which is x to the 2/3. We're going to find its derivative because I'm interested in where is the derivative 0 and where is it undefined. Okay, so the derivative is, I've already taken it for us, 2/3 x to the negative 1/3, which is the same thing as 2 over 3 cube root of x. Is everybody okay with that? Okay, it has no zeros because the numerator is only 2. All right, so what that means is, if I want to know where this derivative is, 0. I want to know where that is 0. What makes a fraction be 0? 0 where? Where? Numerator. Yep, we'll get to the denominator in a second. So the only way a fraction can equal 0 is if the numerator is 0. Is that numerator ever going to be 0? There's no x there. So that's why I said there is no zeros, because the numerator is never going to equal 0. But it does have undefined values because the denominator can be 0. All right, so if I think about 2 over 3 cube root of x, and I want to know where that's undefined, then all I'm interested in is where is this equal to 0? I don't care about the numerator if I'm discussing undefined. So, how would I solve that? I'm going to take 3 cube root of x and just set it equal to 0. What would you do to solve that? Divide by 3. Okay, so then that would just give me that. Yeah, what's the opposite of cube rooting? Cubing. So I would cube both sides. Cube root, cube are inverse operations. They undo each other. And 0 cubed is still 0. So there is one value of x that will make this fraction undefined, and that is 0. Okay, so that is a point of interest to me then. All right, so has an undefined value at x equals 0. So we need to find f of x at negative 2, positive 3, and 0. Why did I say negative 2 and 3? They are the endpoints. Okay, they're the endpoints on the domain. So we have to check, where is derivative 0? Didn't happen. Where is derivative undefined? At 0. Where are the endpoints? Those are the 3 candidates that we're looking for. Okay, so I need to find f of 0, I need to find f of negative 2, and I don't know why I didn't put f of 3 down here. Did it carry on to the next page? Oh, I'll have to change that. Okay, all right, so let's take the original function and plug 0 in. Remember, I rewrote it this way. So if I sub 0 in, and I square it, and then I cube root it, what do I get? 0. No surprise. Remember the graph was at 0, 0. Cube root of 0 squared is a big fat nothing. Okay, negative 2 cube root of negative 2 squared. Okay, well that's the cube root of 4. I don't know what that is, but I'm just going to leave it. Something positive, right? More than 1, less than 2, because cube root of 8 would be 2. And then let's find f of 3. Cube root of 3 squared is the cube root of 9, which would be a little more than 2. Okay, so looking at this, where are my extreme values? All I'm going to do is look at these y coordinates. The absolute smallest of these is 0. So that tells me that I have an absolute minimum here at 0, 0. Even if you don't know what the decimal value of these are, which one is bigger? The one with the 9, right? So I don't even have to know the decimal equivalents. I know enough to know that this one is bigger. So that would be my absolute maximum at the ordered pair 3, comma, the cube root of 9. So what is this one? It might be a relative max or min, but in terms of my absolutes, I know that's the highest and the lowest between those two.
So I thought you said when we set the bottom equal to 0, that's when we find out the undefined. So like for negative 2 and 3, we're just trying to
Okay, so let's go back to this picture. So my interior points will be maxes or mins, possibly, where the derivative is 0 or undefined. But these endpoints are not going to have 0 slopes or undefined slopes. So we just have to test those to see if they're higher or lower than any of these interiors. Okay, so you always check those 3 things. We're going to check where is the slope 0 or derivative 0. Where is the slope or derivative undefined, and then test the endpoints. Because they will not show up on these radars, so we just have to test those to make sure. Now, if the domain is all reals, we don't have endpoints. So we only have to do the slope 0, slope undefined. But if you have a closed interval, then you have to test the endpoints to see if they're the highest or lowest. Okay. Alrighty. So, we already answered all that question. We can ignore that part. Okay, caution. Not every critical point or endpoint signals the presence of an extreme. Okay, so for example, we had this critical point here, but it wasn't an extreme value. Okay, so the extremes are the absolute highest and the absolute lowest. Okay, so let's check this one out. What does x cubed look like? Yeah, normal old cubic function. So it's going to come up like a half a parabola and then continue like a half a parabola in the other direction. Okay, what is our derivative? 3x squared. Okay, I want to know where this is equal to 0. Well, let's set it equal to 0. Divide by 3. Square root. What do you get? Do I need plus or minus? With any other number, yes, but not with 0. Okay, so x equals 0 would be a point of interest for a max or a min. Where is this derivative undefined? Where is 3x squared undefined?
Never.
Never. It's equal to 0 at 0, but it's never undefined. The only time you're going to run in undefined is if you have radicals or variables in the denominator. Okay, 3x squared, I mean, think about that. That's just a parabola. There's no place that's undefined, right? Okay, so this is a point of interest. X equals 0 could be a max or a min. Is it? No. So I did have a point where the derivative was 0, but it doesn't necessarily have to be a max or a min. Okay, and there's actually a name that we use for this point. It's called a shelf point. Doesn't that kind of make sense? It's like temporarily, it just sort of pauses and sits there, and then it continues on. Alrighty. So was it a max or min? Neither. Okay, let's look at the next one. Cube root of x. We haven't talked about that one in a while. What does cube root of x look like? There you go. Got it. It's kind of like turning that cube sideways, right? All right, let's find our derivative. What would the derivative be? Okay, how else could I write that?
Put the x cubed to the square on the bottom.
Okay, what about the 1/3?
It stays.
Okay, 1/3. Denominator is always the root. Cube root of x squared. Okay, so where is this 0? Why? What makes a fraction 0? The numerator being 0. So that's, I didn't even ask you, where is it 0? It's not going to ever be 0 because I don't have the variable up top to set equal to 0. But where is it undefined? Yes. Now I can take the denominator, set that thing equal to 0, very similar to one we just did a minute ago. Divide by 3. Cube it. Square root. And I get 0. Can you just look at that and know it's going to be 0? It's fine if you can. Then you don't have to go through all that. Okay, so this is a point of interest because it's where the derivative is undefined. But look at the graph. Is that a max or min? Clearly not. Like it's hanging out in the middle of everything, right? So it is neither of these. And this one, I didn't draw it. The book tends to draw it a little bit better than I do. Technically, there's a vertical tangent there because it makes that little vertical turn in the graph. It's kind of hard to see the way I graphed it, though. So, yeah, not a max or min. So we are definitely interested in where derivatives are 0. We're interested in where derivatives are undefined, but they don't necessitate a max or min. They're just points of interest. Okay? Kind of like a detective. They are suspects. Okay, steps for finding absolute mins and maxes. Find the critical points, which means find the derivative, set the numerator equal to 0 to determine where the derivative equals 0, set the denominator equal to 0 to determine where the derivative does not exist. And that's, of course, if you have a fraction. Evaluate the function at those critical points that you found up here. Wherever the derivative was 0 or undefined, those are the critical points. We test them. Then we also test the endpoints. Plug them into the function. The smallest of the y values is the absolute min. The largest is the absolute max. Remember to discern, that's a good word, discern, the difference between where the max or min occurs as opposed to what the max or min is. Where, so if the question is saying, where do the critical points occur? Where does the max occur? That's asking you for the x-coordinate. But if it says, what is the max, then that's wanting the y-coordinate. So a good way of getting around it is to provide both. There's an absolute max at 2, 5. So then you're giving where it occurs and what it is all together. So yeah, the absolute min or max of something occurs at x equals something. And then you've covered all bases. All right, so does anybody know what x to the 3/5 looks like?
Oh, looks.
Any idea?
It looks like this.
Like what?
Like this.
Like this?
No,
Like a check mark?
no, kind of.
Like bunny ear or antenna?
Yeah, bunny, yeah.
Okay. All right, so if I rewrote it, I could write it as 5th root of x cubed. Well, we know what cube root looks like, don't we? Would it maybe look the same?
No.
Absolutely not. All right, let's just check and see. We're going to do this algebraically, but we need to see what this thing looks like. And it's not something you should particularly know. X raised to the 3. Oh, goodness. Not that. Let me make my choice there. And I'm going to change my domain as soon as this thing stops creeping along. Okay, what's it look like? It's like a cube root. Similar, doesn't it? Maybe a little more stretched out, but yeah, very similar to a cube root. Okay, so if I want to use analytic methods, aka algebra, to find the extreme values of the function on the interval and where they occur. So find the extreme values, that's the y, and where they occur, that's the x. So I'm basically looking for the entire ordered pair of maxes and mins. Extreme. So absolute max, absolute min. All right, so the first thing we're going to do is find our derivative. Okay, derivative is 3/5 x to the what? Negative 2/5. Or that could also be written as 3/5 fifth root of x squared. Okay, what am I going to do with this derivative? Okay, I want to know where it is 0 and where is it undefined. Okay, where is this equal to 0? Never.
Oh wait, never mind.
Okay. All right, but when is this undefined? That's going to happen, right? When x is what? 0. Can you just look at that and know that x equals 0 would make the denominator 0? Okay. If I put some pluses and minuses under that radical or anywhere else, then it's going to definitely change it. But at x equals 0, I will definitely get a 0 in that denominator. So I don't have a place where the derivative is 0. I do have a place where it's undefined. So this is a point of interest. So are the endpoints, because the endpoints might be the highest or lowest. So what I have to do is figure out what is the y value at all points of interest. What's the y at 0? What's the y at -2? And what's the y at 3? And then we'll literally just look at those 3 y coordinates to see which is the highest and which is the lowest. Okay, so now when I'm subbing in, I'm going back to the original. So you may want to think of that original one as the 5th root of x cubed. Okay, so if I put 0 in and I cube it, that's still 0. What's the 5th root of 0? What's any root of 0? 0. Okay, let's put -2 in here. -2 cubed is what? -8. I have the 5th root of -8. Can we have a negative under a 5th root? Oh yeah, odd roots you can, right? Like what's the cube root of -8? -2. So negative under an odd root is okay. That's going to be a negative number. Okay, if I plug in 3, 3 cubed is 27. I have the 5th root of 27. I don't need to know what these decimals are to tell you which one is the biggest and the smallest. What's the smallest one? Yeah, that one's going to be a negative something. I have to multiply a negative number 3 times to get a negative. And that's definitely the highest. So, I know that my absolute max is at 3 5th root 27. And my absolute min is at -2 5th root -8.
What were you saying earlier? If it was like an even, like if it was like 3 to the -8?
Okay, I was saying that if the root is an even number, then we can't have a negative under there. It's an imaginary. But if the root is odd, cube root, 5th root, 7th root, it's okay to have negatives under there. Because if you multiply a negative an odd number of times, that is a negative. Any other questions on that one? All right, let's look at the next one. Okay, so this one is crazy. We're going to use the graph on our calculator to help us. So use the graph to identify the critical points and determine the extreme values. Okay, let's graph this. I have no idea what that's going to look like. Do you?
Yeah.
You do?
Yeah, I do. But
You-
I don't want to share.
You got it graphed already?
Yeah. In my head.
In your head. Oh, that's so impressive. Is that what that extra bit of sleep did for you?
Yes. Yeah, the reason why I'm not willing to share it is why you're just about to see something.
It's top secret until
No,
now.
No, you'll see why.
It's invisible.
No, it's not. Look at it. That's why I couldn't tell you.
Looks like a butt print, doesn't
Yeah, that's why I couldn't tell you.
Y'all were thinking it too, weren't you? All right, so it's a W. We won't be crude. It's a W. All right, so I want to identify the critical points and determine the extreme values. Okay, now notice on here, I did not limit the domain. Domain is all real numbers on here. Is there a highest point? Not if the domain's all real numbers, because these ends are both going up to positive infinity. Is there an absolute lowest point? Yes, in fact, there are two, and they're going to be the same y level. How do I find them? Ooh, don't use trace. Second trace, I'll buy that. Second trace gets you to all those nice calculate, and we want the minimum. Okay, so this is where you have to move your cursor around. It's asking me for a left bound, and I can do the one on the right or the left, it doesn't matter. Okay, I'm finding the one on the right here. Now I need a right bound, and then push enter one more time, and it will tell me. Now I can tell this is symmetric, so I don't really have to find that other one. I know that I have two absolute minimums. At 1, -3, and -1, -3. Okay, there is no absolute max. If we were to limit the domain, then we would have one, but not with this domain being all reals. Let's go ahead and find those relative, or the relative max. I have one relative max, and where is it? At 0, 0 at the origin. Okay. Question on that one. All right, look on the, oh no. Shoot. I thought I had another paper on there. It got left off.
Oh no.
Well, great. I could show you mine, but it has the answers on it. I know. Let me cover them up real quick. We can get around it.
I'm scared.
Old-fashioned cut and paste. Here we go. All right, so you have 4 graphs of functions, and then you have 4 tables that describe the derivative. Okay, all right, so number 1, I'm looking for a graph that has a derivative of 0 at A and B and a derivative of 5 at C. Can you figure out which one that has to be? Right, let's just talk about 1 for a second.
No. One is C. Yeah, but at
Right.
C. Oh, it's going like you're right.
Raise your hand. 1 is B. Raise your hand. 1 is C. All right. Da da da.
Yay.
All right. 2. I'm looking for something where the derivative is 0 and 0, but then -5. B. B.
I
Okay.
kind of said it weird, not too.
The next one. The derivative doesn't exist. What would that look like on a graph? Corner or cusp, then a slope of 0, then a -2 slope. D. Are we sure it's D?
Yeah.
And by default, but make sure that you understand why this does not exist, and is negative. We're good? Da, da, da. I'll keep my little tabs for next block. All right, that's it.